Welcome back to the second half of Chapter 2. To give you a quick little recap, in the first half of Chapter 2 we talked about how chemistry is a physical science, and we study matter. We study how that material is, what it's composed of, and what kind of properties it has, and what kind of transformation or reactions that it can go through. We also talked about the energy changes that accompany different transformations of matter. So I'm going to build on that, still focusing on matter. The definition I have here for you on the bottom is that matter is anything that has mass and occupies space and can be described as either a mixture or a pure substance. So if you were to bring me a sample of a material that you wanted me to analyze, the first thing I would do as a chemist is I would be interested in, well, is that material you're bringing me, is it a mixture of things or is it a pure substance? Because if it's a mixture, I'm going to have to separate it into the individual pure substances before I can analyze it and things like that. So the first category of matter is to decide whether it is either a pure substance or a mixture. So this flow chart here is going to show you the different ways that chemists classify matter. So I'm going to take us down the right side of the flow chart here first, where we're going to talk about what if that matter is a mixture of components and how you can tell. So the definition of a mixture is it is a type of matter that consists of two or more substances that are physically mixed and they are not chemically combined. Okay, so they're not bonded together. So an example of a mixture would be like salt and pepper. They hang out together, but the salt flakes and the pepper flakes don't bond together. Okay, they don't make a new compound. So two or more substances that are just physically mixed. They have different proportions. So I might, if I was making up some salt and pepper, I might put different ratios of pepper to salt than you might do. So in a mixture, you can vary the composition, vary the proportions of the different components. Mixtures are substances that can be separated by physical methods. So I'll go through a couple of those. So for example, straining would be considered a physical method. You can separate your pasta and water mixture by simply putting it through a strainer or a filter if we were in the lab or something like that. That distillation process that I talked about in the last lecture is another physical process where you can separate mixtures. We call it a physical process because we're relying on the physical properties. So remember, distillation uses the differences in boiling points of the individual components to do the separation. So mixtures can be separated using some form of a physical method. Mixtures are subdivided into whether they are homogeneous or heterogeneous substances. So heterogeneous mixtures are composed of substances that are not uniform. So here is an example of a heterogeneous mixture, this copper on the bottom of a cup of water. Okay, it's not uniform throughout. If I took a sample at the bottom of this cup and then I took a sample at the top of the cup, they're going to be very different. In a heterogeneous mixture, the composition varies from one part of the mixture to another. So that goes along with what I said before, taking a sample at the bottom or the top. The different parts of the mixtures are visible to the eye. So you can actually look at this cup of water with the copper on the bottom and see that it is a mixture of things. So you can see the different colors and things like that. A little bit about the prefix. The prefix hetero means different, and the prefix homo means the same. So this would be a heterogeneous mixture because we can see the different parts. So hetero being different. In a homogeneous mixture, the composition is uniform throughout. So if we look at this brass pot, we can't see the difference. It looks uniform to the naked eye. The different parts are not visible. Okay, so that takes us down identifying mixtures and whether they're homogeneous or heterogeneous mixtures. Now I'm going to take you down the left side of this flow chart where we're going to talk about pure substances. Notice here on the flow chart that pure substances are then further divided into the categories of either an element or a compound. So we'll go through each one of those. So a pure substance is classified as matter with a specific composition. It doesn't have a variable composition like the mixtures had. One category of a pure substance is an element. and you're going to know it's an element when it's composed of just one type of atom. I'm going to back up there a second. The easiest way in this class to decide whether something is an element is if it's located on the periodic table. So in a few slides I'm going to talk about the periodic table, and if I give you a compound and you locate it on the periodic table, then that's going to be a quick way to identify that you're dealing with an element. Compounds, on the other hand, are composed of two or more elements that are combined in a definite ratio. So that's what makes a compound different than a mixture. Mixtures, both of them, mixtures and compounds, have more than two elements or components to them. But in a mixture, those two varying parts are just, you can change the ratio and they're just physically mixed. They're not chemically bonded together. In a compound, you have two or more elements that are bonded together. So for example, water, which is H2O. It's going to have the hydrogen bonded to the oxygen. Okay, so I am going to focus the next several slides dealing with elements, and then we'll come back a little bit more about compounds. Okay. So elements are pure substances, which we talked about. They cannot be separated into simpler substances by just ordinary laboratory processes. So we can take a compound and do some chemical reactions and break it up into the elements. But once you've gotten down to the element, you can't do a simple laboratory procedure to break it down any further. Once you get into nuclear chemistry, we know that we can break the atom down into like the protons and neutrons and electrons and those sorts of things. But in terms of getting down to the element, that would be the simplest form that we can break matter down into in the lab. Elements are the building blocks of all matter. Here's a fun slide. I'm not going to expect you to remember any of these symbols or anything like that, but this for a little piece of trivia. In the olden days, we used to have symbols for elements. So here's a few of them. They assigned gold, the symbol here. Silver had like the moon. I kind of like carbon, just a big old black dot. So nowadays, however, we do not use symbols like this. What we use are these alphabetical symbols, which are going to denote each element. A couple things to know about the symbols. The symbol represents the name of the element. They're going to consist of either one or two letters, and they're always going to start with a capital letter. So that's very important. Some of the symbols are only going to have one letter, in which case it's going to be a capital letter. If you have two letters, then it's going to be very important that you make the first letter capitalized and the second letter lowercase, okay? Because notice here cobalt is a capital C lowercase o. If I had written, let me grab a pointer here so I can write this down. If I write down a capital C with a lowercase o, a chemist is going to look at that and say it's cobalt. If you're the type of student who writes all in capital letters and you don't use any lowercase letters and you write cobalt like this, a chemist is going to look at that and say, oh, this is carbon, this is oxygen, so this is carbon monoxide. This is no longer an element, it's a compound. So it's very, very important that if you're writing the symbol for an element, you do one capital letter and one lowercase letter. Some of the symbols, let me go back to that slide here. Some of the symbols are going to make sense from the name, like cobalt is a CO, calcium is the Ca. They often grab just the first couple letters. Sometimes they grab a couple letters further down, like magnesium is the M and the G. But for most of the elements, the symbol is going to kind of make sense where it comes from. But you're going to get to a few where you're going to say, where in the world, did that symbol come from? It doesn't really, sound like the name. Well, for the most part, those ones are going to be coming from the Latin name. So, for example, copper, which you might want to symbolize as CO or CP or something like that, is actually Cu, and that's because the Latin name is cuprum. Iron, which you might want the symbol to start with I, actually starts with F, so it's Fe, and that's because the Latin name is ferrum. So I'm not going to expect you to know any of the Latin names. It was just kind of a piece of information that students often wonder about. So elements in our body. So which of the four most abundant elements in the human body? So let's go ahead and look at this table. Here are the elements that you find that make up the human body. Here are the element symbols that we just talked about. And this last column is the amount of that particular element in a person who weighs about 60 kilograms. So if you weigh 60 kilograms, you can expect that about 39 kilograms of your body mass is coming from oxygen. 11 kilograms is coming from carbon, 6 kilograms hydrogen, and 1.5 kilograms for nitrogen. And then they keep getting smaller. A gram is a smaller unit than a kilogram. We'll talk about this in lab. So 600 grams is actually less than 1 kilogram. So they've got this table in order where it's decreasing as you're going down. You get down here to the last couple and it's in milligrams. So all I really expect you to know from this slide for test purposes is I do want you to know what the 4 most abundant elements in our body are. So be able to tell me that you know we're mainly made up of oxygen, carbon, hydrogen, and nitrogen. So a couple things I want you to know about the periodic table. As the term goes on, I'm going to be teaching you more and more information that you can get from the periodic table. But for starters, here's just a few things I want you to know. I want you to know that the elements are arranged according to their similar properties. So elements that are in a column on the periodic table all tend to have similar properties to them. Groups or families contain the elements of similar property in the vertical columns. So the elements in the vertical columns are called, we don't call them columns, we call them groups or families. And those are the elements that have similar properties. Periods are the horizontal rows on an element. So we don't tend to say the row, we say, the period number. So here's an example. If we're talking about a group, which is a column, I'm going to grab my pointer back. Okay. We've got a column, and we don't call it a column, we call it a group or a family. You're going to notice on the top of the column is a number, and in this class we're going to be using the number that is either precedes the letter A or B. So this is the 2A group, or the 2A family, and since this row right here is the 4th row down, it's called period 4. Okay, so on a test or a homework I might ask you something like, what is the element that's in period 4 and group 2A? So you'd have to find period 4, group 2A, and you'd tell me that the element is calcium. A quick warning to you is I recommend that you find the period number first. So you count down the rows first before you figure out what column you're in. Because it's very common for students to find 2A first and then go down 4, and they would have said, strontium was their element, because they're forgetting that period 1 just contains 2 boxes, the hydrogen and the helium. Okay, so count down 4 rows first and then find your group 2A. Some of the names I want you to know on the periodic table. I want you to know that the elements in group 1A are called the alkali metals. Now you're going to notice that the first box up here, hydrogen, is very unique. Hydrogen is over here, and I'll tell you why in a couple chapters, but he's an exception. He is actually not an alkali metal because hydrogen is a gas and not a metal. But so with the exception of hydrogen, all the elements in 1A are called the alkali metals. The elements in group 2A are the alkaline earth metals. I want you to know that all the elements down here in this gray region are called the transition metals. We don't have any names for these ones that I'm going to make you memorize. The elements in group 7A are the halogens, and in group A are the noble gases. Okay, so know those names. A little bit more from the periodic table. You're going to notice that there's this heavy zigzag line, which I sometimes call the stair-step line. And I want you to know that the elements to the left of the stair-step, which are blue in this picture, are metals. And memorize the elements to the right side of the stair-step are the non-metals. And elements that you find right along the stair-step are the metalloids. Now, I'm never going to ask you to memorize these, so don't memorize these elements in the green box. Just know that metalloids are found along the zigzag line. Metals to the left, non-metals to the right. A couple properties about metals and nonmetals and metalloids. Metals are shiny and ductile. So ductile means that you're able to draw them into a wire. So I think you're familiar with copper wire. So copper is a metal because it's shiny and lustrous, and it's also ductile because it can be drawn into a wire. Metals are good conductors of both heat and electricity. Nonmetals, on the other hand, are dull, brittle, and poor conductors. Because they're poor conductors, they're used often as insulators. Now, metalloids are, the reason they fall into that category is because they have properties that are similar to both metals and nonmetals. So it's kind of like the chemists couldn't quite decide whether to put them in the metal category or the non-metal category. So they're kind of falling between. So metalloids are better conductors than your nonmetals, but they're not as good as the metals. And because of that, they're often used as semiconductors or insulators. Okay, so where we're at right now on this flowchart is we've just got done talking about elements and their symbols on the periodic table and a little information about the periodic table. I'm now going to bring us back to the last category, compounds. So compounds are two or more elements that have a definite ratio. So like I said, water, for example, H2O. It's always, to be water, it always has to have 2 hydrogens to 1 oxygen. The compounds can be broken down into simpler substances by chemical change. So my question to you would be, if you have a compound and you break it down, so you use some chemical process to break it down further, what is it you're breaking it down into? And hopefully you can see that you're breaking it down into the elements, because a compound are the atoms or those elements bonded together. So you can break a compound down using some chemical change. Here's a couple examples of some compounds. We have sodium chloride, which is table salt, and here's sugar, and we have water. So a kind of a giveaway for a compound is if I give you the chemical formula. So if you see elements written next to each other like this, with subscripts, that's usually a dead giveaway that we're dealing with a compound, because these elements are bonded together. So I like this slide because the two categories that students mainly confuse are the mixtures and the compounds. And I think where the confusion comes is that they both contain 2 different components. So mixtures are 2 components, but they can have a variable charge. Compounds are 2 or more different elements, but they have a fixed ratio, and they're bonded together. So this slide depicts, some of those differences. So if we have a mixture, the mixture we're going to focus on is sugar water, so if we can all visualize that. And the compound we're going to talk about is just water. So sugar water is a mixture because it has a variable charge. Water is not a mixture because it has fixed proportions. Sorry, I said a variable charge. I meant sugar water has variable proportions. You can change the amount of water or sugar that you put together in that sugar water. Water, on the other hand, is a fixed proportion. It's always 2 hydrogens to 1 oxygen. Focus on separating them. You can separate sugar water by doing some physical process. If it were me, I would probably boil off the water, collect my sugar. However, you can't do that with water. You can't do a physical separation of water, but you can do some sort of a chemical change, like, for example, electrolysis can break up water into either hydrogen and oxygen. So notice when you break apart a compound, you're getting down to elements. Up here in this example, when I used a physical process to break apart sugar water, I came down to, you can break it down into just some more compounds. Okay, and then this flowchart is very similar to the first flowchart you had. Says the same things we've been going over, so I'm not going to take the time to go over it, but it's worth you taking the time to read through it one more time. So I've got a couple learning checks just to make sure you're getting the concepts here. Identify each of the following as either a pure substance or a mixture. I recommend that you pause the video right now and go ahead and try answering the problems to the next 2 slides. I'm going to grab my pen. Okay, so we are going to, if it's a pure substance, I'm going to use the variables PS for that. And if it's a mixture, I'm just going to do a capital M. So pasta and tomato sauce. That one is a mixture. It's got the pasta and the tomato sauce, and they are not bonded together. You can change the proportions. Aluminum foil. Well, if you go look on your periodic table, aluminum is actually an element. It's a capital A, lowercase l. So if it's an element, does that mean it is a mixture or a pure substance? And hopefully you would think about that flow chart and say, oh, elements are a subgroup of pure substances. Helium also is an element on the periodic table, and since it's an element, it makes it a pure substance. Air, I don't know how much experience you've had with air. Air is mainly composed of nitrogen. It has about 20% oxygen, and then it's got a small amount of some other components in it. So if you know this about air, you would put down mixture. Okay, a couple things I want to mention. When I make up the test for you guys, I try very hard not to be ambiguous. I try to pick some where it's really obvious to you which way it is. But every once in a while, something will slide through. And I want to stress that I'm the type of instructor that really encourages students to advocate for themselves, okay? So if you feel like you've lost points for something that you shouldn't have, I really would like you to come talk to me about it. So here's an example. I had put aluminum foil on a test one time for students, and I was thinking exactly what I did here for you here. I wanted, the student to think about aluminum being an element. But a student came up to me one time, and they had put down it was a mixture, and I docked them the points, and they came up to me and they said, well, they knew that aluminum foil actually formed this aluminum oxide layer on it, which I hadn't anticipated that they had the knowledge for. So they knew that it had the aluminum oxide layer on the outside of the aluminum, so they put down that it was a mixture, which is 100% correct. So I was able to give them their points back. So if ever something like that happens, feel free to come talk to me about it. Which of the above pure substances or elements? We already talked about that. I might go ahead and ask you further which of the mixtures, identify the mixtures as either homogeneous or heterogeneous. So let's just go ahead and do that real quick. Pasta and tomato sauce. Well, we said it's a mixture, and we're going to say it's a heterogeneous mixture because when we look at pasta and tomato sauce, we can see different parts. If we look at air, can you see different parts with your eye? And the answer is no. So since air looks uniform to our eyes, we would say that it's homogeneous. Okay, so that leads us into this slide. All these here are mixtures, and I'd like you to take the time, pause the video, answer whether they're homogeneous or heterogeneous. Hot fudge sundae, when you look at that, you can see the different parts, so that one is heterogeneous. I'm just going to abbreviate it as hetero. Shampoo, this is an ambiguous one. I put this here on purpose. When I originally had given students shampoo on a test, I was expecting homogeneous because my shampoo that I use at my house is uniform throughout. When I put a little dab of it on my hand, it's just white and it looks uniform throughout. So my shampoo is homogeneous. I had a student come to me one time though and said that their shampoo has flakes of apricot shells in it because they wanted to exfoliate their scalp. And so when they look at their shampoo, they can actually see the specks of apricot shell flakes in it. So he was correct. His shampoo was actually heterogeneous. So he was able to get his points back because he came and talked to me about it during an office hour. Sugar water. Once again, depending upon how much your knowledge of chemistry you have and the saturation point of water, you could argue your case either way. Okay, so if I said sugar water, so you have a cup of water and you put in a little bit of sugar and all that sugar dissolves, I would expect you to say that that's homogeneous. So if all the sugar dissolves, it's homogeneous. What if you perhaps put in like 2 cups of sugar into just a little bit of water? Well, you're going to reach the saturation point where the water can't dissolve any more sugar, and some of the sugar is going to fall to the bottom. So if you have a cup of sugar water and you can actually see some solid sugar on the bottom, then I would expect you to put heterogeneous on that one. Peach pie, that would be a simple one, hard to argue that would be a heterogeneous mixture. You can see the chunks of peaches and the shell, crust, and things like that. All right, well, that brings us to the end of chapter 2.